Be sure to ask questions during the talk. Well, I'm here to talk to you about Venus and partly a quiet revolution that has been going on for a few years. I'm going to start by talking about some science, then I'll talk about two separate missions. One is a real mission, one is a pie in the sky mission. I want to start out with this background night sky. And just to tell you a bit about myself, I've worked in astronomy for 3 decades, mostly working on exoplanets, planets that orbit stars other than the sun. And one of a lot of astronomers' main goals is to try to find signs of life on these other planets by way of gases that don't belong. Our planet Earth has oxygen in huge amounts, 20% by volume. And without plants and without life, we would not have any oxygen on our planet. So there's an intelligent civilization out there with the kind of telescopes we're hoping to build, looking back at Earth, and they see oxygen. They may be able to work out that that's very suspicious because oxygen is so reactive. It shouldn't be there unless there's a continuous replenishment. They might be able to suspect there's life of some kind here. So a lot of my career I spent thinking about what kind of gases might be signs of life on another planet. Because here on our own Earth, it's not just oxygen, but life on Earth, believe it or not, produces thousands of gases. And here's a little factoid for you, somewhat unrelated to Venus, but I just love this and can't help sharing it with you, that on our planet Earth, every gas in our atmosphere to the part per trillion by volume. Think about how tiny that is. If you could grab a sample of an average sample of air and measure all the gases in it, to the part per trillion, every gas is, except for the noble gases, which are not reactive, is produced by life, even though most of the gases have a dominant source that's not life. So take ozone, for example. That, believe it or not, is produced by some life inside some cells. So I was working on all of this, and one of our favorite gases in thinking about exoplanets is a gas called phosphine. I'm wondering how many of you have heard about phosphine on Venus. That's how I got involved with Venus, was I was working on phosphine as a potential biosignature gas. It's on both Earth and Venus, it shouldn't be there. It is so hard to produce. It's what we call thermodynamically highly disfavored. Should not be there at all, nearly impossible to make. Yet on Earth, phosphine is only associated with life. That's a phosphorus atom, P, and 3 hydrogen atoms. So my team was working on, could we someday detect phosphine as a sign of life on another world? When halfway across the globe, Professor Jane Greaves was working on the idea of looking for phosphine on Venus, in Venus's atmosphere, specifically as a sign of life. So I'll repeat it one more time, that on Earth, phosphine doesn't exist without association with life, either bacterial cultures measured in laboratories, found in wetlands and oxygen-free environments, and in animal guts. So it's sort of a different, longer story, but I just wanted to prime your brains, remind some of you about this historic announcement that I was a part of in September 2020. And this announcement of phosphine on Venus became incredibly controversial. Many people just felt, there are a lot of different reasons, and I'd be happy to answer questions on this at the end, but I mostly wanted you to know that this phosphine announcement, despite being incredibly controversial, was a kind of opening of Pandora's box for Venus. It drew attention back to Venus, it brought new people into the field, and it made a lot of people think, wow, maybe Venus isn't so boring and dead after all. So some of you don't know much about Venus. It is super bright in the night sky or the morning sky. It's really bright, by the way, because it has a permanent cloud cover. It's always covered in clouds, fully all around, and these clouds are very, very deep. But most of you, if everyone can mute, that would probably help. Well, most of you probably know that the Venus surface is so hot. It's 700 degrees Kelvin. It's hot enough to melt lead, and it's too hot for life of any kind. But just like here on Earth, if you hike up the mountains, it gets colder and colder. And that happens on Venus as well. Until 50 kilometers above the surface of Venus, the temperature is not that hot. It's actually just right for life. And oddly enough, the temperatures and pressures at about that 50-kilometer mark are similar to what we have here on our Earth's surface. So for over half a century, initiated by Carl Sagan, people have wondered if there's life in the clouds of Venus. Our own Earth, by the way, we have life in our clouds, bacteria. We're talking about little bacteria that could be floating around in the Venus atmosphere. So hopefully you're all with me on this. This idea is still considered out there. And the reason people are very resistant to this idea is because the clouds of Venus are a terrible place. They're very dry in terms of the amount of water available in the cloud droplets or outside the droplets. It's basically nothing. And the droplets on Venus, they're not made of water. They're made of sulfuric acid. This acid is orders of magnitude more acidic than any environment on Earth where life is found. Okay, so we have these two kind of competing ideas. One is that the temperature is right for life, and there is a liquid solvent. The kind of opposing idea is that this environment is too harsh for life of any kind. So here's some basic facts about Venus. It's about the same mass and size of Earth. Its surface gravity is very similar. By the way, a little really odd thing about Venus is, although it takes 225 days to orbit our sun, its day is actually longer than its year. It takes 243 days to rotate around its axis. But on Venus, there's these incredibly high winds at 400 kilometers per hour, and this atmosphere super rotates around Venus in 4 Earth days. Let's see if I have some other facts about Venus. Atmosphere is mostly carbon dioxide with a tiny bit of nitrogen. And it also, this cloud deck I told you about is between 48 to 60 kilometers. That's the range where the temperature varies from about, now we've switched to Celsius, 80 degrees Celsius to 0 Celsius. And that is my brief summary of Venus, of where we are so far. So there's something really interesting been happening. And by the way, I've divided my talk into thirds, just this short 1/3 on science, slightly longer third, 2/3 on missions to Venus. Now, I did want to tell you about some really brand new work, and it's going to be hard for me to convey this because I can't see you. I don't know like the context of where you're at on your knowledge of Venus, but it's not perhaps the hellhole that everyone thinks it is. And these sulfuric acid droplets that are so toxic, they would burn a hole in your skin, actually might not be so bad after all. And there's some really brand new work going on. It's not the point of my talk tonight, but it's just breathtakingly amazing. And I just wanted to tell you the tiniest bit about this. But these sulfuric acid droplets that, according to the current thinking in the planetary community, is that they're sterile, that no life of any kind could survive. But we have two really interesting results, not me personally, but people that I've helped encourage to work in this area. One is that if you put a small hydrocarbon molecule into sulfuric acid, it will be a seed to a very rich hydrocarbon organic chemistry. We think that in these droplets, organic chemistry can happen, and that's needed for life. It doesn't mean there is life, but it opens up the possibility for life. Now, these sulfuric acid droplets, they'll destroy any kind of life. However, we and others have started to find that certain chemicals are resistant to sulfuric acid. In fact, this one group at Harvard has managed to generate a sphere made out of a self-generating spherical membrane made out of fats, out of lipids that are resistant to sulfuric acid. So there's a lot of new work going on in this area. And I encourage you to stay tuned, that's the whole entire motivation for the missions I'm going to be talking about, is that these cloud droplets are not sterile. The idea that there could be rich chemistry inside and maybe even life in the droplets. Now, what is really interesting about Venus is there are some decades-old chemical mysteries, atmospheric anomalies, we call them. And for our purposes today, it doesn't so much matter what they are. I have a list here on the side. But the fact that there are some outstanding mysteries. Remember I talked about oxygen on Earth? We have 20% by volume made by life. Well, Venus also has oxygen, not 20% by volume, a tiny amount, tens of parts per million, tiny amounts in the cloud layers, but enough to be completely unexplained. And the cloud particles of Venus, by the way, sulfuric acid is a liquid at the temperatures and pressures of Venus. And if it's a liquid, it has to be more or less a sphere. It can't be a crazy shape like a snowflake or some amorphous blob. But some of the particles in the atmosphere have been measured by space missions that went to Venus in the late 1970s to be not spherical, actually, and to not have a known composition. And that leaves room for more complicated materials to be inside the droplets. So that concludes the science part of my talk. Okay, so Venus appears to be a crazy hot world. In the cloud layer, the temperatures are right for life, but the chemicals are very, very harsh for our Earth life. So what I did a couple of years ago after the phosphine discovery was I assembled a team of people to work on the idea of missions to Venus that will purposely search for signs of life, of Venus being more habitable to life than we expect, or even life itself. And you can copy this link and you can download this 120-page report we wrote. And this report was sponsored by Breakthrough Initiatives. Now, there's a lot of activity in other parts of the Venus community. During all of this phosphine and this work I show you in this slide, NASA decided to go back to Venus and selected 2 missions. So for the first time in nearly 4 decades, NASA will be returning to Venus. ESA, the European Space Agency, also decided during this time to send a mission to Venus. None of these missions will be searching for signs of life. It's too taboo, it's too crazy. And besides, there's no flexibility to change instrumentation, even though those missions aren't planned to launch until later this decade. So in this mission study, we came up with 3 ideas. We, just for lack of a better way to explain it, we call them small, medium, and large. Small is like short term, medium is medium term, and long is long term. And today I've decided to tell you about the small mission, short term, and also the long-term mission, which is our sample return. I know which country is next. It's the USA and New Zealand, because that's my small mission. My small mission that I'm proud to lead the science team and science instrument on. We have partnered with Rocket Lab. And do all of you know, I'm assuming, Cole, that everyone here knows what Rocket Lab is. And we actually have a tentative name for our mission. We call it Morningstar. And our Morningstar mission has a target launch date of May 2023. So those of you who know about Rocket Lab, you know that their niche is relatively small rockets. And so Rocket Lab plans to launch from New Zealand in May 2023. That's our target. We have a backup date of January 2025, 18 months later. And Venus will launch and it will send its photon appearing out of the upper stage to be our cruise vehicle. And the cruise vehicle will take 4 months to get to Venus and will just bypass Venus, but before it bypasses Venus, we'll drop off a probe. That's shown in the background here. There's the photon and this little, it almost looks like a UFO, unfortunately, but it's gonna go hurtling down through the atmosphere of Venus. This is a cheap, small mission, relatively speaking. There's no parachute. It'll just go down and like at 60 Gs, and will take about an hour to go down. It'll eventually implode or crash land. But this mission aims to have 3 minutes in the cloud layers of Venus. So we're given 3 minutes for our science payload and less than a kilogram. So we did a lot of work to narrow down what instrument could we build on time and what instrument could do potentially breakthrough science. Okay, that's a tall challenge. We did pick a great instrument with our instrument builder, Daryl Baumgartner. And this instrument, it sounds kind of complicated. I'm going to walk you through everything, but we call it an autofluorescing nephelometer. And we want to search for, remember what I was telling you? That these cloud particles of sulfuric acid, they may not be sterile. They may have organic compounds. And we're going to look for those organic compounds. So when we describe a space mission, and perhaps you've had a seminar like this before, we try to be very purposeful and intentional in the way we talk about it. We have goals, objectives, and we try to trace that down to the instrument requirements. So our goal is to search for signs of habitable conditions and signs of life in the clouds of Venus. We have 2 main objectives. The third one's in gray because we might not reach that, but we want to detect organic material in cloud layer particles. And our second objective is to seek anomalous cloud components. I did mention before that non-spherical particles may indicate that well, non-spherical particles definitely indicate that the particles are not pure sulfuric acid. There's something more complicated going on. Anyone here seen a science traceability matrix before? What we do is we write all of our objectives down on the left, and it flows across to detailed instrument requirements. I'm not expecting you to read all of this or to understand what it all means. I just want kind of you to know that it's there. And it can actually flow both ways. So for example, we're given our data. We're not, in this case, allowed to, unfortunately, tell our engineers how much data we need to transmit back. Instead, that comes from the right side of the diagram. We're told that we have no communications relay. So we are transmitting direct to Earth from this probe. And we don't have a lot of data bandwidth. We don't have a lot of bandwidth. We can't transmit a lot of data back. You can see here, it's about 400,000 bits of scientific data and housekeeping data direct to Earth. It might be a bit more. So just to go from left to right for a second, we're searching for the presence of organic material. And this eventually flows down into what wavelength we need, what kind of laser we need, et cetera, et cetera. So rather than boring you with the details of this table, I thought I'd walk you through a few things about this mission, and also in the sort of framework of the science traceability matrix. Objective: search for the presence of organic material within cloud layer particles. Our rationale is that fluorescence is the way to detect, but not identify, organic material inside cloud droplets. On Earth, many compounds are known to fluoresce when subject to ultraviolet radiation. Now I'm showing you on the right here, ringed molecules. Okay, so these are like, where at each point, there's a carbon atom. It's not shown. It's just for some reason the way that organic chemists want to write down chemistry. But see what these weird dashed lines mean? They mean that the electrons are delocalized. So unlike an atom where the electron is strongly bound, in a ringed molecule of carbons, the electrons are kind of shared amongst the carbons and therefore loosely bound. So if we send an ultraviolet photon directly to a ringed molecule, it's not too hard to eject that electron to a higher energy level. And when the electron cascades back down, it emits a photon of a different wavelength. We call this fluorescence. For those who aren't as familiar with atoms and molecules, think about if you've been to a nightclub or a kid's fun house when there's a black light and like your white clothes might light up purple. And that's fluorescence. And that's what our instrument is going to do. It's going to shine an ultraviolet laser through a window in the probe out to the particles and measure any fluorescence that occurs. Now on the top, there's a picture of real laboratory experiments showing in a solution of 90% sulfuric acid and 10% water. Look, they put a tiny piece of a meteorite and they showed that under ultraviolet, it actually fluoresces. If you look here on the far right, that purple light and blue light. So to support this, the team led by Steve Benner and Jan Spacek did experiments. And what you're seeing on the right here is the excitation wavelength. So that would be a wavelength of like an LED or a laser. And this is nanometers. So these are mostly ultraviolet wavelengths. And this is the emission. It shows where a whole bunch of different molecules emitted radiation. So what you're trying to look for here by eye is where's the densest clump of points, because we don't know what molecules, if any, right, are there. And we want to kind of maximize our chances to see fluorescence. So you can see there's two clumps. We picked this middle clump here, which dictated the parameters of our instrument. So we decided to settle on 440 nanometers for our laser and intensity of 470 to 520 at some value to be determined above the background illumination. So actually, it looks like we chose this top blob. Okay. All right, so we are, our second objective that's related is just, you may not know this, but no particle in nature scatters light equally in all directions. Every particle has a weird way to scatter light. And on the top right here, we're trying to show you, if you imagine the direction of incident light going from left to right on your screen, every particle has different ways of scattering. This is showing you Rayleigh scattering from like a small gas particle. It scatters mostly forwards and back and very little out to the side. There's other things called Mie scattering, where light comes in, it mostly wants to forward scatter and very little sideways or backscatter. But if you can measure the polarized backscattered radiation, you can actually tell something about what the particle is made of. And that's the second thing we're going to do. We're going to measure with this ultraviolet light laser that's going to shine out through a window. We're going to see the backscattered polarized radiation into a certain angular range and use that to discriminate amongst different particles. I just wanted to go back to this slide for a second and look at this plot for a moment. I just wanted you to appreciate that we did real lab work to inform our instrument design. Okay. So here's a little bit about the instrument. It's just a schematic showing you, you have to imagine that the bottom kind of square is our instrument inside the probe. And then this dark blue line is the probe wall. The white here is the window. So we have a laser shining out of the window, out into the airflow past the vehicle skin. And we are imagining, or not we're imagining, we actually have two separate detectors. One is to detect fluorescence, shown by this green. We're imagining a particle lights up and fluoresces. And then we also have this other detector to direct the backscattered polarized light. And this is showing you that, this will happen continuously for a few minutes, and the data will be transmitted back to Earth. So more of the chart, which I won't go through the details, flows to mission functional requirements. And I just picked out a few key points related to science to convey to you. When we sort of think very carefully about how this flows, we need to have nighttime entry because we're trying to measure fluorescence and scattered radiation. So we need to reduce our background light as much as possible. So nighttime is important. I already mentioned how data volume is challenging for science return. And another main issue we have actually is we have a problem with, we don't want to have a problem, but we know from many past missions, the Russians sent like over a dozen missions to Venus, probes that went through the atmosphere. We don't want, as our probe like hurtles through the atmosphere, some of the material could ablate off and it could recondense and cover our window. So we need to cover the window and or heat the window so we can make sure our window is not going to get covered with particles. Okay, I think I'll skip this third one since we're probably not doing it, but the summary of this small mission is it's a new instrument, new science in a small package. This is a brand new paradigm for missions. Our Morningstar mission is the first of its kind, privately funded mission with just sort of a singular goal, one instrument. And we have a chance for revolutionary discovery, rich organic chemistry inside what before were thought to be sterile cloud droplets. So for the last part of my talk, I'll jump from, instead of like a mission that's actually happening, that the instrument is almost built, the rest of the mission is being built. We have our target launch date of May 2023. I'm now going to switch topics to what was advertised, which is the Venus sample return. This is far in the future. And I've left out this kind of whole rationale and thinking that when we want to find life, signs of life itself, perhaps by way of, okay, pardon me for like the complicated term, but morphological signatures, like actually seeing a cell-like structure. If we want to find very complex molecules, we thought about this a lot, and we do believe the best way to do it is to get a sample return of the cloud particles, because our laboratories here on Earth can interrogate like the same particle over and over again. We have incredibly sophisticated instruments, and it's really, really hard to do any kind of similar science robustly, repeatedly from a balloon platform, cruising through the clouds. So this sample return idea is not new. I'm sure you've all heard of sample return for Mars. People want a sample return from Titan and other things. People have thought of sample return from Venus before. Typically, they want to go down to the surface, scoop up some material, go back up to either like an airborne laboratory or go home. And here's a cartoon outlining what it is we imagine, just very basically. So we imagine a launch. There's the cruise phase to get to Venus. Then we separate out two separate things. One is our orbiter that's going to orbit Venus. The other one is the entry vehicle. The entry vehicle, we're at number 6 now, will go into Venus and we'll deploy a balloon. It looks upside down here, so you have to maneuver this in your brain. And this balloon is big. And attached to the balloon is the instrument that collects and stores the sample from the atmosphere, perhaps up to 1 gram of solid cloud particles and liquids. And we'd also like to bring back some atmosphere. But what has to happen is attached to the balloon is a Venus ascent vehicle. And when the instrument is finished collecting material, it will rise up as high as it can go, where it gets easier and easier to launch. And this vehicle will launch and we'll have to rendezvous with the orbiter, transfer the sample, and then this orbiter will come back to Earth and we'll recover the sample and go from there. So most of you might know we've already returned some samples, stardust from a comet. The Japanese have gone to an asteroid and scooped up some sample and brought it home. NASA's OSIRIS-REx mission went to an asteroid. Do you remember that? It scooped up some material about a year ago. It's on its way back. And those didn't have a rendezvous. They just went, grabbed, and came home. But we do obviously rely on NASA and Mars to figure out this hard part, how to rendezvous with the orbiter before coming back. So I picked a few things to tell you about. This just shows a few details of the entry in a little more detail. So going from A through I, we have the parachute that slows down our entry vehicle. The balloon system gets released and the initial parachute is dropped away. The balloon inflates, it does its job, sample collecting. The canister gets secured for this Venus ascent vehicle that prepares for its launch from the balloon. It launches up, goes as high as it can. Like I said, this is showing 66 kilometers. We sometimes think about 70 kilometers above Venus surface, rendezvous and gets back. So I wrote a proposal to NASA. NASA has one branch of out there far futuristic ideas, and we got selected to be funded. And what I'm telling you now is what's part of this proposal. So we decided to push forward on 3 of the least mature components. And these I've listed here for you are how we're going to capture the sample. What is this ascent vehicle going to be like? And we also have to think about how big does our balloon have to be and how massive does our ascent vehicle have to be? Isn't this very ambitious mission best managed as a national mission, given its mass, complexity, and cost? Maybe. Maybe it is. We'll see what happens. So for this mission, we don't have a plan to fundraise right now. We're working obviously on our first mission. We have a second mission underway as well. But Cole wanted me to talk about this mission, so that's where I'm at right now. We'll see what happens over time. I want you to imagine that we find that particles fluoresce, that I get to carry out my second mission and find very, very complicated biochemicals existing in the Venus atmosphere. We might be motivated to do this sooner and faster than NASA and other governments could possibly do. In fact, when I advertise my collection of Venus Life Finder missions, we do like to say public-private partnership. Okay, so I don't have any answers for you here. This is more of what our goals are. We're scratching our heads on how to do sample collection. This is not a solved problem. When people think about asteroids and Mars, you're scooping things up or collecting rocks. This is different. Particles are liquid. There's perhaps some solid particles floating around. We work with a company called Honeybee Robotics, who have a tape sampling material. They actually have gold is somewhat sticky. And it's showing you on A here, it's lettered A, this feed spool, where it just kind of collects material and then spools back in on of itself and collects material that way. In terms of liquid, we have a couple things we're going to try under this proposal. And there are 2 concepts that people here on Earth use. One is passive. Fog harps. You can Google fog harp later and see that in some regions, people put these giant wires and droplets adhere to these wires and then drip down and get collected at the bottom. Call this a fog harp. You can use a fan. Imagine using a fan on Venus to, send the droplets your way. On Earth, people also use active cloud samplers. We've only found kind of massive, power hungry ones, which is kind of complicated, but we're still working on this. And there's some text on the side there for you to browse. So what we're doing is we're studying the spooled sticky tape collector. We're making a basic design, and we're considering viability of material in the sulfuric acid environment. In terms of the cloud particles, we're investigating the feasibility of both active and passive collectors to see where that will take us. Okay, so this Venus ascent vehicle is just notional at the moment. We're going to try to develop this one a little further during the year. So right now we're imagining our Venus ascent vehicle is a 2-stage solid propellant rocket. Can launch up to 10 kilograms of payload, but we still can only collect a really tiny amount of material because this payload is like the storage and the casing and the whole thing that has to come back through Earth's. It's just the whole collection and the whole storage container. And yeah, here's just some details about it. What we're doing now is we're doing some feasibility analysis. How massive does this Venus ascent vehicle have to be? And can any size balloon like hold that mass, actually? What will this do to the balloon? You know, we have this balloon in the gondola. Will the gondola be swinging around too much? What will it really look like? So I don't have any values for you right now, but just wanted you to know we're trying to work on this. So, you know, here on Earth, we have balloon-borne atmospheric science is very common. People send balloons really high up to do astronomy, even to try to do X-ray astronomy, to get high up above the layers of the atmosphere that block high energy particles from reaching us. People study the cosmic microwave background from balloons. There's lots of things going on, but in terms of using a balloon to collect and store, in terms of using a balloon on another planet, has only happened one time, and that is the Russian Vega missions in the 1980s. Russia sent 2 balloons to Venus, and these balloons went to Venus with batteries. They lasted for about 48 hours. They sent data back. They were amazing. They were just fixed altitude, whereas ours has to go down and go back up. We work with a company called Thin Red Line. This is a real demonstration of a, it kind of looks like a bunch of pumpkins stitched together. There's a variable altitude balloon that can go to different layers of the Venus altitude. Okay, this is a bit detailed, but if you know, this is recorded and you can screen grab. But we basically had to, for this proposal, and that's what I'm sharing with you now, is we had to make a detail of where are we in all of this technology and where are we going? And so that's what this slide explains. And let me just think if there's any really important point that I want to share with you. I don't know, I'm personally really fixated on the way that we're going to collect the liquid particles. Here we say that there are commercial products, they're too bulky, too power hungry, and they don't work very well with the small particles that we really want to get down to, because, you know, here on Earth, our smallest life forms are like 0.2 microns, which is really tiny. So we need to be able to capture the smallest particles out there. Okay, so this is a summary of the sample return. So for my last slide, I'm just going to summarize where we came from and where we're going. We have studied Venus for decades, if not centuries, right? And probes that went to the Venus atmosphere nearly 40 years ago found some amazing things. You know, they found that these droplets are sulfuric acid, but some of the droplets appear to be different. And those are called mode 3 particles. I briefly mentioned that in addition to these unknown particles, there are a range of gases that are unexplained, including oxygen. We now add phosphine to that list. This phosphine discovery, and I'm happy to answer more questions about it in the Q&A, it motivated a flurry of new activity, including revisiting old data, including my team emerging, we think maybe including the NASA and ESA selections. But our future for Venus is definitely going to be bright. There's a lot of activity, a lot of great things just waiting to be discovered. Thanks for coming.
Hey, thanks so much, Dr. Seager. We can open up have an open discussion and have any questions and answers here.
Sure. Hello. Is my audio coming through?
Yes, we can hear you. Go ahead.
I apologize. I joined late, but look forward to reviewing the rest of it. I'm Daniel Tompkins. I'm both professor of Mars agriculture with Mars University. It's a 20-hour course on that. But I also lead an X Prize team for rainforest conservation, in which we're using dirigibles, inflatables. And one of the ones that we'd like to deploy is variable lift inflatable. And I was looking at the wind speed on Venus, 224 miles per hour. Are you familiar with the variable lift inflatable things?
With what you're doing or what?
Oh no, just in general, as far as it gives you a lot more lifting capacity if you are considering tethered architectures.
Yeah, I'm somewhat familiar with it.
Okay. Do you see any application for that for kind of a tethered? I guess, do you see the feasibility of a tethered airfoil on Venus?
You mean tethered to where? Like tethered to where?
Tethered to the surface.
Not really, because the surface is so difficult, and the area that we're interested in is like literally 50 kilometers above the surface, and the surface is so hot, and like electronics can't work there and things like that. So not right now.
Okay. Yeah, I was curious on the mechanical approach. I know there's been efforts to develop a mechanically resilient system, and I was thinking if you had a dirigible with variable lift, if that would be a solution kind of to, because I know a lot of those deploy, right? Photovoltaics don't work. You know, you almost have to have a wind power type of system for that. I didn't know if there's any current efforts underway.
Yeah, I'm not sure about, I don't think I have a good answer to that question. Yeah.
Okay, thank you.
Sure.
So, Sarah, can I ask a question about the science on the first mission, which is to me kind of cool because it's so simple and small, right?
Right.
So if you look at the autofluorescing nephelometer and the results you can get from it, if it comes back with perfect results from your perspective, how much of the data comes back tells you that it could be life, or it's still ambiguous and you need the second mission and the third mission and so on?
Exactly.
If you get partial results, then what happens? Because I seem to remember from your VLF document that the organic material could actually be quite generated abiogenically. So I'd like to get a sense of, from what you're looking at when you say the mission is going to be, if it's going to be a success, and let's hope it is, the data that comes back, what would you be able to say about it in terms of, yes, it's indicative of life, no, it's still very ambiguous, and so on and so on. So if you can give us more of that perspective.
It's a great question, and it's really helpful because our perfect data will be ambiguous. Our perfect data will tell us that there's organic chemistry in the droplets, which itself is a breakthrough, but we won't know if that organic chemistry is due to life being there, or if it's, as you said, abiotic. That, for example, a gas or a small part of a meteorite got into the droplets and set off a chain of reactions that led to this organic chemistry. We won't know, but that's all we, but the goals of this mission, are to send the first mission. It's a small, cheap, fast mission. So honestly, it will really just kind of pave the way for the next mission.
Okay.
The one I didn't talk about is what we really want to do. That's a bit complicated, but I'd be happy, if you want to know, I'll just tell you briefly, because all the questions you're asking are the same ones we've been asking ourselves. And this next mission is much harder, but we want to go back with a mass spectrometer, an instrument that can tell you what the molecule is, just in terms of its mass and, just in terms of the mass and something about the structure of it. And the mass spectrometer would tell us what kind of organic molecules there are. And that would help us go between, is it just some random organic chemistry, or is it more likely to be a life molecule? So we would have to do something more. This first mission, in its perfect success, would be life-changing in a way, paradigm-changing, from, remember, the sterile droplets to, wow, there's actually chemistry in these droplets. but it won't tell us if there's life.
So it really is just a way of, a good result would be to say get enough interest to actually get the second mission underway, right, with the balloons and
Yeah, that's a good way to look
testing.
at it. Mhm. That's a good way to look at it.
Okay. Well, thank you
But,
for
you
that.
know,
I appreciate that.
Yeah. Mhm.
Hey, we're also wondering here, these these wind speeds are a bit mind-boggling in terms of comprehension, and we're curious if if there's what the potential turbulence is like in the 300 to 400 kilometer per hour winds, and how such turbulence in the whichever X, Y, and Z direction might impose challenges for, potential bacteria cluster formation. And
Okay. Actually, I thought you were going to say the real challenge of all that is how do we point our balloon and our Venus descent vehicle so it has a chance of matching up with the orbiter. We haven't worked on that. That's probably our biggest problem. I see what you're saying, though. We haven't really thought about that in terms of the bacteria clustering or not. It's, yeah, maybe an interesting question. I don't know. I guess I do tend to think that these winds, overwhelm any other substructure, but I don't really know the answer to that. And very few people do work on the dynamics of the atmosphere and what's really going on there. So good question. I'll have to file that one away for later.
thank you.
I wonder if for orientated you could deploy a drag and then have some variable lift airfoils to that on the other two vectors. So you could kind of have a drag vector and then two kind of 45 vectors to then stabilize it.
Good idea. That's a great idea. I'll bring that back to the team and see what their thoughts are on it.
Another question on the utility of CO2 to plastic production in situ, or hydrogen for providing inflatable gas to fill it with. Both of those seem to be capable of being made out of the atmosphere. Doing kind of micro balloons as part of a filled architecture, so that it's not just one membrane, but actually multiple small membranes that are all in situ produced from CO2 to a polyethylene plastic, if that's appropriate. I'm not sure if it is.
Yeah, that's awesome. I really love your ideas. We have entertained and encouraged so many people to write up their ideas for lots of ranges of missions. I love the idea of, dispersed elements, not perhaps for sample return, but as a way to probe so much of the atmosphere. And I haven't heard this one before. We're more thinking of dropping off tons of little mini probes that are deployed from the balloon that might transmit back through the balloon. We hadn't thought of a lot of little balloons and what job they could do. They could last a lot longer than mini probes that are deployed. I mean, there's room for so many great ideas.
Maybe even for an ascent vehicle, you could just produce all that plastic in situ. NASA has done this inorganically, producing from CO2 directly polyethylene and plastics. I'm also the founder of Grow Mars, which is pioneering an expanding loop process using bioplastic in a way of basically taking one plastic greenhouse, growing a bunch of biomass in that, and processing that through to more plastic to make more greenhouses and more building material. And also, so that's where I'm a little bit familiar with the capabilities there. But
I mean, it would be amazing
Venus,
if you have amazing if you could imagine some kind of self-sustaining mission architecture on Venus and just be monitoring it for long periods of time.
Yeah, I mean, inorganic for kind of sustainment on Mars and really anywhere off Earth other than Venus, maybe. Having that bioplastic expanding loop seems to solve a lot of problems. Also, just when you have a lot of food being grown, there's a lot of inedible crop waste that you have to process and do something with it. So whether you take those chemicals through to more plastic greenhouses, or you take it through to more lab consumables or hydraulic oil or whatever you need, it's still this big base chemical feedstock that you can take through to a lot of other mission supplies. But it seems like the inorganic approach, as it's slower than the bio-derived approach, seems to fit really well with this architecture. Unless you're going to grow inflatable greenhouses on Venus, which I'm game for that too.
Cool. Okay, here's a good question. I can't imagine a suitable mass spec would add more than 10 to 20% to the total mission cost. Why not include a mass spec in this first mission? Finding life might add a lot of money, interest, I expect. Well, our first mission is a really cheap mission. I don't even know the total cost. I know the cost of the science team and the instrument, but I think this mass spectrometer, to finish building it and to make it work in sulfuric acid. And one more thing I'll tell you in a moment, that is the cost of our entire mission now or more. So it's not just adding 10 to 20%. It's like the cost of the mission just for that instrument, or that might not even be enough. So the problem is that most mass spectrometers, all mass spectrometers that have so far flown, they suck in material and they pyrolyze. They heat it up until it's a gas, and then they analyze it. But we have our eye on this new type of mass spectrometer for space that doesn't do that. I don't understand exactly how it works, so I can't tell you, but they don't pyrolyze it. They get a sample of liquid or solid. It has to be solid. So we have to evaporate the liquid, and they use a laser to analyze it. So if we're not just sucking up everything, we actually have to find out how to deliver. Okay, so as I'm talking, I'm realizing that that maybe I have to change my mind. So that's a good question. Thank you. So what we want to do, and then I'll switch to what my thinking is on this really good new question. So, is if we want to do the way that when you heat everything up and then do the mass spectrometer, you lose a lot of information because you don't know exactly what the parent thing is. What is that molecule that might be life? Because you vaporized it now. And you have to do a lot of kind of detective work to get back to what are the options for the parent molecule. So we don't want to do that. We really want to go to Venus, use this fancy new one that's going to cost a lot of money to finish. And not only that, how do you're floating around in a balloon. We have to still have to collect the liquid and solids, right? And deliver it into this mass spectrometer that also has like a vacuum chamber on the inside. So we're kind of stuck there. We're working on this now, actively working to solve this. But now, thanks to David, maybe there's a way. It is laser desorption. It is laser desorption. So I don't know what Malditoff is. This could be a similar instrument that's different. The team we've been working with is from Switzerland, and they call theirs Origins. But yes, it is a laser desorption mass spectrometer. So perhaps we should put David's idea back into the mix, because we could go pretty soon. People know how to build these mass spectrometers. We wouldn't need a balloon to fly around, so we can figure out how to get the solid and liquid sample. We could just drop a probe, suck stuff in, and measure it, and it could be cheaper and easier. So yeah, great job. Great question. Yeah, really good question. So yeah, thank you. Yeah, Raman spectrometer. We haven't worked with Raman spectrometer, but yeah, we know what Raman spectrometer are. They do definitely also leave some ambiguity, but you're right. What I love about this group here today, so David and Daniel and others, is sort of that burst of creativity and like sharing all those different ideas. That's exactly the spirit of this new Venus initiative. You know, all ideas are welcome. All ideas are good. We can't possibly implement every last idea, but they're all kind of floating around, and there's just so many possibilities. So our host has left now, so I guess I can host, but are there any other questions? Maybe someone who hasn't asked a question yet, someone maybe who normally doesn't speak up wants to ask something.
Hey, Sarah, I'm an exoplanet hunter by training now, and I have to say that intrigued me more than just Venus. I know Venus is close, so we can see that, but taking that, you know, those same thoughts and maybe using the JWST as an opportunity to look at the atmosphere. I think you saw those recent readings from WASP 94, I think, WASP 94b. Again, you know, I was thinking, wow, if we could see something else in there, just another compound of some kind or another gas would be spectacular. Phosphine, when Dr. Greaves made the big announcement, I was quite excited. And still, even though it was such a very small reading, still excited. And do you think we're still going to get those really tiny numbers?
Well, see, you've almost answered your own question in the way you described phosphine. It's kind of heartbreaking in a way because it's so tantalizing, but it's such a tiny signal and required so much data analysis. The more data analysis you have to do, the kind of worse the situation is. And we're going to be seeing that, in my opinion, on the web, the James Webb Space Telescope, where hundreds of people around the globe want to observe a small rocky world to search for signs of life that don't, gases that don't belong, that might be a sign of life. But phosphine is, to me, that's partly why I work on Venus, because that was like a lesson learned. It was like a career crisis. We find a sign, and the same thing will happen with the web. People will ask, is the signal real? And they'll fight about that. Then they'll ask, is the signal really attributed to the gas, phosphine, or whichever gas the team says it is? Yeah. And then if they agree on that, they'll say, well, is it really made by life? Or what about the numerous unknown non-life possibilities? So I used to be, or maybe I am still as excited as you are, and I work with Webb. My team is going to get data on TRAPPIST-1e, but we got bumped until July of next year due to perhaps internal politics, which I can tell you what I think it is. People learned how to scam the system, because when you propose to use the James Webb, you have to write down, you're an observer. So like when, you can't observe all objects all the time. Sometimes the sun is in the way. Sometimes you get bad weather. But with the Webb, you tell them when you can observe. And the team that's observing all the other TRAPPIST planets, if you can actually, all the proposals are public, so you can look at them. Yeah. They said they could only do June, July, or August. But transiting planets, they keep transiting. They transit forever. So you can, anytime. So we can observe like anytime. And I guess the schedulers did it automatically. And so we got bumped because we said we could do it anytime.
You want me to call Carl for you? I'm kidding.
So yeah. So anyway, we are excited about the James Webb. People are working on that. That's a whole other talk, but people are confronting models, data analysis tools with real data now. And it's not pretty yet, but I'm sure papers are being submitted or have been submitted, and we'll wait and see.
Yeah, I think Venus excites me more. I love the fact that you've gotten to the point where you are at an atmospheric level that, maybe we can get some really good readings. So I'm really hoping that all happens. Rocket Lab will make it happen. I don't know, Peter seems to have his stuff together, so yeah, let's hope. Daniel, I see you're off. What's up?
Yeah, well, one question, and maybe I missed this at the beginning of the talk, but the Russian probes that were sent, Venera, if that's the right pronunciation, what's the chances of those introducing a biological element? Like, I guess, what's the risk profile if something were to have traveled between Earth and there, given the types of materials and the likely common biologicals that were on it? Has anyone done a risk analysis for how likely those would also survive in the atmosphere of Venus?
Just 1 second. I was about to sneeze, so I had to take a break, but okay, so that's a really good question. And sometimes we joke that the reason why people are so resistant to the idea of life on Venus is if there is life there, we believe there is, we have to change how well we sterilize the outside of our spacecraft. Because NASA has a planetary protection office, and we want to follow whatever the rules are. But depending on the planet, there's different levels of cleanliness, like your spacecraft has to be. And so that question that you asked is kind of known, actually. How well do you have to sterilize the outside to get there? But it's a good question, and we don't yet have an answer, because most of our biochemicals cannot survive in sulfuric acid. They will react, they will be destroyed. But we're finding that some of them can. And so sort of one experiment on the to-do list is to take a bunch of cells, put them in sulfuric acid, and see if anything survives. Because it would be terrible, yeah, wouldn't it, if we sent our mass spectrometer and look, we find these biochemicals, yay, but then they end up being the one part of the cell that might survive. So we haven't done that work, but you're right on with that question.
And more like all the materials that went into that spacecraft and its thermal zones and everything, like what's the chance likelihood that past probes accidentally cross-contaminated way back when? It'd just be interesting.
Yeah.
Like, oh,
I wouldn't worry about past probes
because
because the past probes went 4 decades ago. So I'm not worried about past probes because I think everything's going to be recycled, like new cloud particles will form. So let me just take the last couple minutes to answer some of the questions here. So there's someone from Tartu Observatory in Estonia. Hello. Perhaps you work with Mikkel, Professor Mikkel Pajusalu. He's part of the team actually, and he's working on an instrument to measure the acidity of the droplets, because there are like other theories that the droplets are not as acidic as we once thought. And this ties into the question from Rob. He sent me a direct question. What extremophiles on Earth do we think are most similar to what might be found on Venus? The answer is none. The cloud droplets on Venus, the ones that are sulfuric acid, they are many orders of magnitude more acidic than the most acidic environments where life is found on Earth. So if you picked up an extremophile that lives in very acidic environment and brought it to Venus, it would not survive. Okay, so how about we take this one, 2 more questions. Have we been able to decide on target locations where atmospheric analysis is most likely to take place? It doesn't too much matter where from our viewpoint. We just want to, for our first mission, go on the night side so we don't have contaminating light from our sun. For our balloon mission, there's one place we don't want to go, one region. We don't want to go near the poles because we think Venus has a Hadley cell, an air circulation cell that rises at the equator and goes to the poles and then comes back down in like a giant cell. We don't want to get trapped in that cell. We want to be somewhere where we can just get whipped around by the winds. We don't want to get drawn down where it's hot because everything will stop working. Maybe you missed the cost. I didn't mention that. And the cost, we don't really talk about it because we don't totally know. I can tell you how much the science team and instrument cost. Not much. I'll say, let's say less than $1 million. Most space instruments are on the order of $30 million. In terms of the rocket lab part, I'm not party to what the fund costs are, but you might be able to find out on your own if you try to figure out how much does a rocket launch cost, how much does all the different components cost. But if I had to guess, I'd say that for Rocket Lab, it's an opportunity. I think they got private money from somewhere, but it's an opportunity to demonstrate that they can go to Venus. And this is like a good investment on their part. And if they can demonstrate they can go to Venus, I would speculate that means, later they could get contracts and get money. So I think there's sort of a lot of different reasons we're doing this on the cheap. A lot of people are putting in their own time and things like that. I think that comes to the end. It's 8 o'clock now, and I get to go do something really fun every night when I'm at my summer cottage, which is now. We go down to the beach at sunset, and we're on one of the Great Lakes, and we face west. Probably only Terry can guess what I'm about to say. And it's really windy today, so all the particulates are blown out of the atmosphere. And every night we look for a very special phenomena called the green flash.
Yeah,
how many of you have heard of that?
It has been busy.
If you haven't heard of the green flash, then next time Terry needs to explain that to all of you, because it is one of the most beautiful natural phenomena that exists. When the sun sets, think of it like a rainbow. It refracts due to the density of our atmosphere. And if you have a long path length, like from an airplane or a mountaintop or over the ocean or a Great Lake, that sun actually becomes a rainbow. And as it sets, if you do it right, the last thing you'll see is a flash of green or blue if you're young. Because, all the other colors of the rainbow are blocked by the earth and you just see a flash. You can't see it every night. When the sun goes down, that is way too fast. That duration of that green shining is so little, you'll never see it unless there's a boosting effect. And the boosting effect happens from, not to make it overly complicated, but if you have a thermal inversion, like, when you drive on the road in the summertime and it shimmers, it looks like there's water, but there's not. We get that here because the water can be warmer than the air. But if you see the sun looks a bit distorted, that's good because it stretches out that green. So someone sees it in San Diego many times. That's amazing that you guys see it. I sometimes go to San Diego, but we don't see it.
We get it here on the coast in San Francisco all the time.
Oh my gosh, you see it. Okay. So I have to go now because it's time to get ready to go down.
Go.
Yeah.
You're brilliant, Sarah. Thank you for the time.
Great meeting all of you, and good luck with your university.
Yeah, cheers. Thanks a lot.
Bye.
Y'all be safe. Bye, everybody.